Good morning, everybody. Thank you for the invitation to talk. My background, just to introduce myself to people who don't know me, my background is in engineering. I'm not an arborist. Over the years, I've given many presentations and workshops on trees and different things, particularly the forces and the structural analysis of trees, different countries. And I've been asked, well, what's an engineer do that's different to an arborist? I think the short summary is engineers measure things. So if I'm looking at a tree, I want to know how high the tree is, or how big it is, or how much it weighs. When the wind blows on the tree, how strong does the wind blow? And prior to that, I was an agricultural engineer. I've worked in Africa. I spent 12 months in Sudan on agricultural projects with the World Bank. I've worked at Werribee, just up the road, with the Department of Agriculture in the old tractor testing days, which doesn't exist anymore. And in those days, we'd test tractors and we'd put sensors on tractors and see how strong and big they were, particularly cabs. We'd drop a 2-ton block of concrete onto the cab to simulate they were tipping over. So when I came to arboriculture and worked at Burnley, and I came in about 1991, I had a lot of this skill set that then when computers came in and technology and sensors came, to me it was quite simple to put these sensors on trees. And no one had done that before. And what I found contradicted everything I was reading in the literature. And in particular, I got inspired in 1999 when Klaus Mathek came out here and he wrote the book, The Body Language of Trees, and from that, the axiom of uniform stress. And I started studying this seriously, and I found out what was missing in this book, which took me about 2 years of study, and I'll talk about that today. So that's the background of where I'm coming from. I was also told today there'd be about 90 people, half probably how I haven't seen before. I used to lecture at Burnley, so a lot of ex-students here, and hello to all of you. I always say they survived my lecturing in spite of what I taught them. And today I'm going to challenge your thinking. That's my objective. Rather than teach you something, I'll teach you, and from what I learned on agricultural aid projects, really has influenced my style of teaching. In Sudan, we were helping poor, starving people during Ethiopian famine on an agricultural project. And there was a saying in the projects, if you give a man a fish, you feed him for a day. If you teach him to fish, you give him food for life. So I'm going to show you where you get information today on tree structures and forces. And hopefully, I haven't got time to teach you it all. I'll show you some things and from that point you in the right direction. And if anybody's interested to follow up, I'll be happy to do that. So the introduction is, what forces cause failure in the structure of a tree? And in Marybeck, I'll show you, which is the renamed Moorland Council in Melbourne, a tree fell under no wind conditions this year. No one was killed or injured, but it was, we'll talk about that. And I'll show you some Sydney storms. This is from 17th to 18th of January this year. Over 1,000 trees fell, and they recently had another big storm. So it's quite a topical issue. So in Marybeck, a tree fell over under no wind conditions on the 7th of January. The owners had previously complained to the council. The tree was inspected, was reported safe, no action was taken, tree falls over. So these are some of the images. I didn't visit this tree. I thought I'll just save this for in case I get invited to talk again, because it's quite topical. So that's what the tree looked like in the ground, and there's the tree that had fallen over onto the house there. So I was thinking, so what are the forces on the tree, and can we measure something to help assess the likelihood of failure? You know, so obviously this is this year's situation. What are we doing about it? And the tree was inspected by an arborist. It was assessed as not showing any signs of instability or structural issues. And if you read That's what the council said about it, that we value the community safety and take it seriously. Our response is we immediately send a crew out to clean up. Please, if you've got any concerns, contact us. So that's sort of the typical council, what does that say? And the people held up the arborist report. So I know a lot of you present reports, and the arborists said the perceived danger that the tree will fall in a storm has not been established. So the arborist had written and signed off on that tree that fell over. So I'm thinking, where are we at with our technology to be able to analyse a failure? So that's sort of the introduction. Then the Melbourne-Sydney storm, these are some dramatic pictures. I know a lot of you spend time in Sydney, and Sydney has these southerly busters, these east coast cyclones that really rip into the city. My son rang me up. He's sick and tired of hearing me talk about trees, but he rang me up. A tree fell over near my house. So this was a photograph he took near his house. So these are just some examples of trees and the small root plates in the nature strips, and all these trees must have fallen over in a big wind. They're old, established trees. What can we do? That's the situation facing us, and we're really just subject to what we've always been subjected to, these tree failing in wind. So what are the forces and what can we do about it? And we're still working on it. So how am I going to present this to people who are not engineers? I'm not going to be able to give you a 4-year engineering course in an hour. Over the years I've tried to do that. I presented last year, and at the conference I had COVID, so it was remote, and the feedback was, oh yeah, it was good but a little bit academic, and I come from an academic background, so okay. So I'm trying to make this presentation a little bit more practical. I won't read that, but that's sort of to guide you if you want to go back, what did we cover? I don't know if this presentation is going to be available to you later. And I know many people have seen this before, so I thought I'll just explain it. Some people haven't. What's going to happen? This is a tree being removed. An arborist climbs up a tree, he's got a chainsaw, ties himself off, and he cuts the top off. What's going to happen? And perhaps I haven't communicated what I'm on about over the years quite clearly, and this is the situation arborists find themselves in, is looking at a situation beforehand and trying to analyse the forces, and you've got a lot of training in the area, you think you understand, but what you're looking at is a static view. And one of the things about the trees in wind is it's a dynamic situation, and the dynamic forces aren't even present when the static view is there. Dynamic forces are not there for you to see. So it's only once we play the video that you see the dynamic forces come into effect. So I haven't practiced this too much here. So this is what happens. Cuts the tree off, top falls down, hits there, and he gets flung around so much he nearly got flung off and nearly died. So what was happening, I'll just stop that. What forces are created in this situation, or more importantly, and this is the objective I have today to try and get you to see this, what's not there? What's missing in that? Pardon? Damping. Okay, damping. What's damping? Damping is a term used to describe when energy is used up, when energy is dissipated. You can't create or destroy damping, but it can distribute it. So what's not there is damping. So in arboricultural terms, what's not there, after he's cut down, all the branches have been removed. So what's missing are branches. And that's really a take-home message of today. What's happening in this situation are the branches are being removed, and branch removal means damping removal, which you can't see until the wind blows. So most people have seen that, but not everybody's seen this one. This is a United States video version of what I've just shown you. So you know something's going to happen. Here's a guy who's cutting his teeth. There's a big tree and this is a limb that's extending over the neighbour's boundary. He's tied off, he's secured, he's tied in. He's going to cut that with a chainsaw. So in most of my presentations, I show the video and say, oh, wow, yeah. But now I'm giving you a challenge. There's a static view. You can't see any dynamic forces because they're not there. Okay, so what's going to happen? It's going to fall off. The branch is tied on, same situation as before. It's going to shake, we know that. There'll be some reaction and movement, we sort of know that. So this guy's experienced arborist, he knows that's going to happen. Tied on, here we go. Got a little speaker here. Okay, so now we can see some dynamic forces, and if you don't understand them, you can get caught out, and they're really even life-threatening for in this situation. So you cut off all the branches first, right? And then you cut down the tree, right? Yeah. And then this lady said, but I don't know what she's saying, but it shows some close-up of the before and tying on. He's doing everything pretty right from what I can see, but he's just got no idea of what's going to happen, obviously. So he used a heavy rope. Well, that's not going to make any difference. So all that energy of the tree branch falling, all the branches have gone, there's no damping, all that energy has to go into the human, into the other mass. I'm going to talk about mass damping. So what's happening there is all that energy that's stored up like a spring and this is talking later, so he didn't die. So, and the other thing I should mention is in today's world, things are different. Teaching is different. Presentations are different. I'm trying to get all this stuff on the web or at least in your phone so you can use it and see it and take it back later. I don't have those skill sets, so one of the things I'd like to do is get this sort of presentation not just videoed as we are now, because no one's going to sit through a half-an-hour video, but so you can take it away on your phone. So if anybody likes to follow up and try and get that as a resource for everybody to convert this with some sort of arboricultural or engineering explanation of what's happening, we can do lots of little short clips rather than an hour's presentation, because I probably won't get through all this anyway. Okay. So that's an explanation. Because of time, I won't read what I've said, but basically that's words. I usually spend time on that, but I won't now. But what are the dynamic forces? There are two. One is inertia. That means things keep going when they're going. Like imagine a train going and a car goes over the intersection and gets wiped out. You know, the train's mass is so big, its inertia, it can't stop. If you know anything about ships, you know, a big tanker will take about 5 miles to stop. Or, you know, so that's inertia. What that means is big trees, big branches do different things to small trees and small branches. It also means some of the research, if I got a chance to show you, you can't do a test on a small tree and scale up the results. In statics you can, in dynamics you can't. The other one is damping. Now damping only occurs when there's movement. Damping is leaves on branches and attached, and damping is complicated. It's hard to get a message across. There's aerodynamic damping, which is the drag, which is the wind, which you know about, but then there's other dampings like fluid damping and mass damping, which is what I'm trying to show today. And I'm going to try and move on. Please stop me if I'm going too fast or anything. So here's my third test. Now this is inertia. This is the other dynamic forcing. There's no damping, we know that. What's inertia? Big and small. I used to, when I tried to get this concept, I've used an image of Godzilla because his catchphrase was size matters. And that's my catchphrase, size matters. And my presentation today is not about small trees, it's about big trees. It's not about forest trees, it's about trees that you see out the window. You know, I guess I'm saying about 15 to 20 metres and bigger, which are good to. So here's a big tree being demolished. This is a French Sato in the background. And this is probably, my estimate would be about 2 tonnes of tree being chopped off. Hard to see in the screen, but it's being supported by a crane on top. And the arborist is behind at the moment in this shot. You'll see him in a minute. He's also tied on to the above crane, not to the stump and not to that. So we've got a big mass and they know it's going to fall over and they're all prepared for it, and it's going to be caught by the crane and he will be attached on the crane. All good? Okay, this is a static view. What's going to happen? Now look at the small mass. It's not controlling things, it's the big mass is controlling it. And if the big mass squeezes the small mass between the trunk, that's not going to be pretty. So this is an example of big and small masses, 2 masses interacting, and the big masses dominate and the small mass doesn't really have much effect. And the dynamics, you can't stop it, you cannot stop it. The inertial forces make that big mass unstoppable. And you know that anyway, but this is sort of an engineering presentation to try and separate this force from that force to that force, and to try and give you a visual presentation of it. Okay, that's enough. So now let's have a look at wind in trees. So I'm just putting this to paint the picture of what I'm talking about. I'm not talking about the trees out the back in still air conditions, which is when arborists evaluate them, because the dynamic forces are not there. You can't evaluate them, you can't see them, they're not there. They're not being taken into account. But in wind conditions, you can see this is a bifurcated tree. And when we talk about the tree canopy, is the canopy working as a unit or separately? And even those separate canopy sections, there's 2 there, are those canopies working together or are they working separately? The branches interacting? So it introduces that concept of sail area. Is it a sail or not a sail? So at the moment, basically all I can say about that is it's complex. So if we talk about dynamics and swaying, we've got to start somewhere. So engineers start with a simple sway motion. That's where we're starting from. It's a starting point. It's not an end point, it's a start point. And that's not a tree, it's a vibrating pole. Okay, it's got no branches on it. And this is perpetual motion because it's a computer, and that will never stop because it's just a little image, and it's going backwards and forwards. But that gets into people's brains, and I see Ben's going to talk later. Is your father here today? No. Oh, I can tell a story about him. So Ben's father's Phil Kenyon, and I said in one of my presentations that the trees don't sway backwards and forwards like that. They do sway, but they're swaying downwind and they go like this. And Phil, in his very eloquent way, said, "That's bullshit." I've spent 20 years lying on my back at lunchtime looking at the big mountain ash up in the Dandenongs, and they sway backwards and forwards. So I had a big argument with him, and it took him 2 years to come in one day to the staff room, and he said, "I think you might be right." "What about?" He said, "About the trees swaying." Because when you look at trees, you have no reference point. You don't have a fixed reference to see it swaying back. They don't do that. So and all my measurements show the tree sways downwind and sways back and comes back. It doesn't go backwards and forwards, but some do, and particularly palm trees do. But anyway, so that's our starting point. Now, if we go and look at wind tunnels and we have streamlining, we get concepts like drag coefficients on solid objects, that's where that comes from. And it's been in the literature, even on the front cover of a university in Germany in September 2003. That was their front cover. That is a concept that is published and seen, and images are there, and I'm saying that is far from the truth. And you get arguments with people because they'll show images like that and they say, no, well, that's not. But what's happening is that tree is perfectly adapted to its wind environment, and it's a static concept, and this is constant wind. So in wind tunnels there's constant wind, so yes, the air's moving, so you can say it's dynamic, but it's really static forces, and that's a static adaptation, and there's no movement of branches, there's no damping movement. Now if you want to use calculations, and I'll show you very briefly where to get those calculations. I act as a consultant and I do the calculations, but all the calculations are based on solid objects and wind tunnel tests. And the drag coefficient of a tree, if you're wanting to find that information, you go and look up a reference. I've even been an expert witness in court, and you look up the list and you give the reference. All of those references come back to this reference of what's called Mayhead 1973. Mayhead 1973. All the drag coefficient work, there are one or two exceptions, but go back to this in 1973, but no one's ever read the paper. So I read it. Data were available from two experimental runs on in a 24-foot wind tunnel at Royal Aircraft Establishment Farnborough in 1962 and 1967. This is published in 1973. He's using 10-year-old data that he never even got. He processed the data. He talks about this. It's a very good paper because he says, don't use this information. He actually says that. The tree height was in the range of 19 to 28 foot. Okay, right, all right. So I'll draw a diagram. The yellow is the dimensions of the wind tunnel. There's the tree, and the 28 foot, he says that some of the trees were sticking out the top of the wind tunnel. So his experimental method was very, well, not his, but the data was coming from some experiments in 1962, way before computers, and that's the basis for most of our calculations, and we don't know if they're right. So this is from Rudnicki, another one, a Canadian guy, and all the wind tunnel tests by necessity use small trees. Now that's going into predicting wind loads using computers, taking an image of the tree, drawing the canopy, calculating the sail area, calculating the steady state winds, and doing wind load calculations coming from Germany. And that's becoming codified now. That's a very powerful image, and in Germany this is becoming the normal. This just goes back to in 2003 I started a PhD. I got a grant from the ISA in America. I was told by some people who've become very good friends, you're never going to get a grant from Australia, you've got to get an American partner. So they're not going to give money to someone they don't know. So I partnered up with Dr. Brian Kane, who was the keynote speaker at the conference last year. So that's been a very fruitful partnership. And we purpose-built in 2003 some instruments that we stuck on the tree, connected to a computer and got all the data. So this is the early days of computers and technology. And they're the trees, they're pictures of the trees I measured, most of them around Burnley. And are they the same shape or not the same shape? It's really just the message I'm getting across today. And this lecture came out of a conversation I had with Lockie, and saying, look, we talk about trees, and the title of this is Trees, Structures and Forces. What is a tree? You know, the trees are so much different shapes that I think these trees with many branches are behaving differently to other trees. So now this is the theory, and this is the practical. So the theory, I've made a theoretical model of trees with masses and springs and dampers to separate them. Now that model is just a way to describe it, it's not a tree, but that's what that model says. So all the mathematics and the theory is saying that trees do this. That's step one, but we go further. So we'll show you some real trees falling over. This is from New Zealand. And my question here is, did the tree fall over all at once like we see there in the video? And this is New Zealand driving rules. Don't worry about cleaning it up, just Don't even, oh, the traffic lights are out, so. But what I'm trying to show in that video is this is the end point. We have actually measured this. If trees fail first in one route, then another route, then they rock for hours and hours, possibly from one storm to the next, and then they fall over. And this is sort of this idea of how the tree's failing progressively over time leads to the concept of measuring something, and the tilt sensors, which we'll be talking about later in the conversation, in the presentations today, is maybe if we measure how the tree is tilting in the winds, we can begin to understand how whether it's stable or it moves from a most stable to a less stable to a critical level. So that's the concept behind the tilt sensors that we've worked on. Now, damping and mass damping, this is my theoretical model of a tree with branches to show the contribution of this mass moving, that mass moving. But then on the tree there are other little masses and little masses and little masses. And this is a picture of a tree near where I live on the Yarra in Boroondara. And I published this in the Western Chapter Journal. The Western chapter of the ISA from California is the Western Arborists. I met the editor at another conference I was invited to in Hong Kong last year. And she said, oh no, that sounds really interesting, write an article. I said, what about? Oh, whatever you like. So I thought, okay, I'll try and get this damping and mass damping across and I'll get some feedback. One person emailed me and he wasn't really interested in that, he was just asking another question, he used it. So I thought, oh, maybe I'll use it too. I don't have to write another article and maybe you haven't seen it. So with Shane, we've put it up on the web and he said, oh, you better check copyright. So I emailed back the editor and as always happens, she's left the job. Oh, I'm never going to get an answer. But they're pretty switched on there and she emailed me and then the current editor emailed me and said, yeah, you're welcome to use it. And they're really encouraging and I found them fantastic in supporting what I've been doing, both with personally, I've met Matheny and Clark. They're really, really good people. And she sent a message to say, look, they really encourage you to network with them. And I said, I'm talking to 90 switched on arborists in Geelong, which is a technical hub that's rapidly developing, and it is. Geelong's really rapidly developing. Land prices are going up quickly. So I think we're on the cusp of some really interesting stuff, and we have the ability to take our ideas and move them forward into some future additions to arboriculture and the knowledge. So the next part is, where do you get information from? So if you were looking at tree risk assessment, now this is not everything to do with arboriculture, this is sort of specific in the field of assessing risk, assessing wind loads there. Where do you go and get information from? Could I have a show of hands? How many people have at least heard of VTA? Visual Tree Assessment. Okay, most people in the audience. That's useful feedback. Where does VTA come from? If you had, oh, I'm using it, where does it, anyone? It comes from this book, which is Mathick, 1994, The Body Language of Trees. And I'll go through it briefly. This seminar started out with Lockie and me saying, why don't we invite people to bring their book and we'll go through it. Then I won't have to do any presentation, you can see it in front of you and take it home. So, okay, so that's what I'm going to talk on in the next slide. Other ones, not everything, but other ones are QTRA, which is common. I really retired full-time from arboriculture just before COVID hit, so there might be new ones coming out, so I'm not 100% up to date. And the other one is the ISA BMP, Best Management Practice, published by the ISA, and it's a US guide for arborists. It's not scientific, it's pretty general, but it is the document that the ISA back, and if you were going to court to justify what you were doing and you could say it's in there, it's a very useful document to be able to justify what you do. Most of you will know what's in there anyway, but it's just sort of, these are the best management practices. It's not a code, it's not a legal thing at the ISA, but they're just doing it to try and get things up to date. That was published in 1994. Most people arboricultural knowledge on forces are 31-year-old information, and we'll go through that to see what's in it, what's right, what's not, and in particular, I'll give you a challenge, what's missing. There's something missing it. So this is the body language of trees. If you want to go and buy a copy on eBay, the cheapest one I found was $338. I was talking to Paul Whitten this morning and he said, oh, he saw it for $1,000. I looked in my copy and there's a pencil mark. I paid $80 in 1990 for it. It was a rip-off then, and it's still a rip-off. It was expensive then. So I guess not many people have it. So I thought I'd tell you who Mathic is. If you go and see Mathic, or if you hired Mathic to give you a talk, he will charge a return business class airfare and $10,000 per seminar. He gives seminars in Germany and charges $10,000 for an audience like this, and regularly gives them. He's very powerful, very wealthy, very influential figure. He always dresses the same, in black forest gear with light tan boots, sunglasses and a page boy haircut. He's a very unusual character. He was born in East Germany and was taken by the East Germans. After the Second World War, Germany was divided between East and West. The East Germans were a very authoritarian group, and he's put in a East German prison for over a year and survived that. And after the Berlin Wall came down, he came to the West. So he's got a great personal survival aura about him. He's a wonderful character to meet, but a difficult person to talk to. So his ideas are here, and the background to her ideas are about survival. I think probably personal, and how trees have survived and evolved. So they come from a very good base and background. So what's in the book? And what's missing particularly? There's the axiom of uniform stress on page 13. Visual tree assessment on page 119. We're not going through it today, I haven't got time. Static pulling test, is it good, is it bad? It's in here. Wind loads and sail area. Wind loads equations and the fractometer. Most of it, I would say, is wrong. There's a little bit in there that's right, but it's taken many years for me to say that and to establish what's wrong. Now, if we go to the axiom of uniform stress, how many people would say they've heard of the axiom of uniform stress? I'm just looking for, have a look around, because a lot of people have. This is sort of fading out, but it's been a very big influence on how we think trees grow. So how many people would be confident in being able to quote the axiom of uniform stress? What is it? You know, you're arborists, you're in business, you're going to court, you're acting as a witness, we're using this reference. Okay, and you ask, what is the axiom of uniform stress? People think they know, so I thought, let's just photocopy the book and have a look at it. On page 13, it's actually on page 12 to 13. The axiom of uniform stress is a precept. What's an axiom? What's a precept? Which seems obviously true by virtue of its inherent plausibility, but cannot generally be proved. He's saying that. It's what he says. An axiom is sort of a self-evident truth. We all know it's true, right? Well, it's not how we work. And specifically down the bottom it says, this is the quote, and I quoted this for years and got told by Phil Kenyon, oh, that's bullshit, because I used to call it the axiom of uniform surface stress. No, that's rubbish. He says, basically a bit of waffle, an optimal structure has a uniform stress over the whole of its surface. It is not talking at all, or doesn't specify in that, at all what's happening inside the tree and the stresses inside. Doesn't pretend to. There it is. So it's been misinterpreted terribly. And this body of language of trees is a wonderful book and gives you good insight into trees, but it's talking about the adaptive growth of trees. It's taken this idea, which is wrong, into adaptive growth. This book, the BMP published by the ISA, does not mention the axiom of uniform stress, but in Appendix 3, it talks quite a lot about adaptive growth. So that adaptive growth sort of has given this legitimacy, but that's been well known way before Mathick and will be way after Mathick. So this has had a big influence on people. So this is from the BMP. So this is a simple, these are the forces on trees. This is sort of my lecture from 5 years ago. I'm not talking about it today. If a tree's bending, it's tension on one side, compression on the other side. There's a shearing stress, which is a sliding stress in the middle, and also torsion. Nobody's yet measured torsion, but I've developed a method if anybody's interested, and it's simple, and I think it can lead things further forward, but doesn't need many resources. And that's on ISA BMP page 80. So what I'm saying here is, when a tree's in the wind, it bends and the stresses on the surface are not uniform. Okay, so how does Mathick deal with that? He says the wind then will blow on another occasion from the other direction and in another direction. Eventually over the seasons, the tree will have a uniform loading, so that's why it grows round, because if it's not loaded uniformly, it grows on one side, and you've seen a picture of that. So his explanation has been over the years, and it's buried. I saw it, but I lost it again, that on average the tree gets loaded equally. Well, no, it doesn't. So, and I could take you through some scientific journals that they've had a big debate about 10 years ago. Say, oh, it's all bullshit. So, and I've given this, no, I haven't given this presentation, but I have given presentations in Germany. So that was about 8 years ago. So I'm even more confident now. If you want to go to VTA, there it is. An explanation of where it comes from. It's been modified over the years. It's probably good to go back to that, and it's visual tree assessment, and we probably haven't come much further in 31 years. But here's something I want to sort of point out very obviously. That's the full page, and that's just a note. This is the sail area concept. Now what this is saying is the tree acts like a sail. Go and read it, that's what he's saying, and all his work's on that. And I mentioned the equation of used in wind tunnels. That's the equation there. So if you want to use that and sort of do the calculations, that's a very good reference to use from there. But is it right? Is it true on trees? So how can I say that's not correct? I say it in these terms. What's missing there? Firstly, it's a very static situation. So dynamics is missing. There's no dynamic forces at all. There's drag, you know, the air's blowing, you know, that's dynamic, it's moving, all the airs, but you picture a sail, it's under constant loading and there's no branches. So that's the sort of thing that's missing. If you want to look at the pulling tests, that's another in chapter 11.1. Now it says in the pulling test, this is where I agree with Mathick, that the pulling tests will not predict failure. They're an excellent diagnostic tool, but you're doing a static loading, you're not doing any dynamics, you're only testing the trees. I've had to cut a lot of slides out for time. Most of the static pulling tests, and I've been with them in Germany, I've been with them in America, we do it here, we cut the top off the tree. And I said, why do you cut the top off? He said, oh, the instruments take a long time to settle down and it's quicker to do it there. And logically in statics, all the load goes from there down and we're not measuring up to it. That's true. But I'm saying, well, that's all the dynamic stuff. You're missing all the good stuff that they don't. Other things in this book is the fractometer. When I left Melbourne University, I worked for a tree company, and one of my first jobs was to use the fractometer and get it working. And I'd previously worked on forestry projects at Creswick on internal growth stresses of trees. And I said, it doesn't work. And he said, bullshit, you're going to work on it anyway. Some people might know where I was working and understand that. So I did, but it doesn't work. So there's a lot in this book that just doesn't work. Now this cost well over $1,000 and he sold many of them and it doesn't work. Why doesn't it work? It takes a core sample from inside the tree, like you take a core sample from inside a concrete column or something, they do that. Then you take it and orient it with its grain and twist it and bend it and measure it very carefully and look at the forces. The reason it doesn't work is when that core is in the tree, it's subject to internal growth stresses. And once you remove the core, those growth stresses release, and then you're testing something that isn't in its environment. So it just logically, it's not testing the material, the core material, in its working environment. It's testing it out in its unstressed environment. So the logic behind it is not very good. So what's missing in Mathic is branches, damping, and there's no dynamics. And the consequence of that is, static says, if I did a little model here of a static pulling test and pulled it, I could scale up results and we'd go outside and we could scale that up. So it's actually saying that small trees and big trees perform the same. Dynamics says they don't, because other things come into play. Now the ISA BMP is what I would recommend. It doesn't mention the static pull at all. It does mention it's a companion to the standard, so that's where it sits. It's very useful guide. You take it or leave it, but it's at least you can point to something. And it does mention the adaptive growth. If you look at the acknowledgement of people who have made contributions, my name's in there, and it's the only Australian name in there. And this is the 3rd edition, so I've been pushing and pushing and pushing. So my contribution is in an appendix, and I said, well, you've asked for my input, if it's worth saying, why don't you put it in the text? Why do you stick it down the back? And there's a paragraph on damping. I've got a slide later, so I won't go into it there. So damping is, it's probably my career's work. I've got a paragraph in there. So but 31 years old, and there's a lot of things that aren't right in there. A few things are. It's influenced us. This is 2025, and it's moving on. So I think just as a visual representation of my lecture, that's where we've come from, and this is where we're heading. So you can go and get those books. So here's another picture, I think, just to set the scene of what we're trying to do. How do trees fail? So I think we should be, if we get a chance, take more videos, stick them on YouTube, because we can get a lot of technical information from videos now. So I'll just let you watch that and observe. Basically, I'm asking, is the failure sudden, or is this happening over many hours? This is obviously a tree of many years' age. Has it been subject to some weakness, some digging, some instability, and can we measure it? So then it actually falls over quite gently. And then you can see the root plates and that sort of thing. Well, have a look a little bit more, but I'll just see if I can play this again. Okay. Firstly, have a look at the branches and the wind. Are those branches moving upwards or downwards? Have a look. I have measured branches in winds. I've published it, not many. I don't know anybody else has. Even eucalypt branches leaning down never go down. They don't. Oh, that's rubbish. I've seen them go down. You have a look at the videos closely. What's that saying with, weight reduction on limbs and branches if the wind loading's upwards? I could tell you many stories, and I'm yet to find evidence of wind blowing branches downwards. I started this saying, oh, well, the branches obviously goes up and down like that, then this big one comes and it breaks off. Shigo says, have a close look, that most branches blow upwards, and this is from Phil Kenyon. Have a look at eucalypts after a windstorm. All the branches are downwind, and the windward branches break upwards and stay over there, because the downward branches don't get wind loaded.
They're already used to the load.
Depending on the direction of the wind. Because yes, they are used to it, but if the wind direction, and we often get a lot of failures in Melbourne and Dandenongs from the easterly, which isn't the strongest wind, but it's the unusual wind. Yeah, so I'm not necessarily giving answers today, it's more about questions. So we're now moving into the realm of engineering and mass damping. So I thought, what do engineers do when they look at failure analysis of buildings that fail dynamically, which is earthquakes? And my supervisor was an earthquake engineering expert and well into mass damping, and a lot of my PhD work is using the mathematics from earthquake engineering on multi-storey buildings, which do fall over. So what engineers do is they build models to see what they do, and they put them on shaking tables, and then they analyse the buildings and look at the stresses and forces. And I sort of taken that methodology and put it into trees. To me, it's a good chance to try something in nature. It's nothing unusual. So I could leave all the maths out. This is visually what we're doing. We're shaking a structure on a table. Then we put an absorbent, we put a mass damper in it. So the mass damper is that mass up the top is a pendulum, and you can see it's not an aerodynamic damper, there's no wind blowing, there's no, like a bicycle pump or a piston, there's a hydraulic damper, it's a mass damper. So there's it shaking without the mass damper. So the mass damper is sort of doing this. Hop on a swing, a child swing, and try and stand there, but you can do this because you keep your balance. There's a balancing act happening. So specifically, a mass damper is a mass that's tuned to the building, and it's only a small portion of the big mass that minimises the dynamic sway at a particular frequency of the building. And it's used in buildings. I've given lectures on Taipei 101 in Taiwan, has a 700-tonne mass swaying in the winds. But I thought I'd update that. But this is just a simpler way of looking at mass damping. Now, if you were engineering students in an earthquake engineering practical, you go out to a bridge and you jump up and down and you shake a suspension bridge. Then you go and design a mass damper and you put a mass that's able to move and it's secured under the bridge. You tune it, you do calculations, you tune the mass of the bridge, find its frequency, work out what size mass and what frequencies it has, stick it under the bridge, secure it, no electronics, it does it automatically. Then you jump up and down and that's the effect. And you zoom in here, the light's not too good, and if you can see very closely, this mass underneath is moving up and down fractionally. Can you see that moving? Just going up and down a bit in that frequency. So that's a tuned mass damper. It is conventionally used in engineering. I could give you lots of other examples, but I'm not. So if we look at trees, what are the mass dampers on the trees? What are the little masses that are moving to prevent the big mass shaking? It's the branches. And some, even this, the palms on the palm tree have some mass damping, and it's not one or the other. There are the other damping, there's the aerodynamic damping, the drag forces, the wind forces. I think there's hydraulic damping in some very flexible. These are not stiff, rigid steel concrete structures. These are flexible structures. So there's internal damping. And it's basically a tree is an optimised structure that has taken hundreds of millions of years to get itself perfect. That's how I view that structure of a tree. So over nature and over time, it's optimised itself. And our job is to understand it. So let's have a look at the small trees. Now this comes from Ed Gilman's work where he built a $200,000 wind blowing machine, grew trees for several years and blew them over, but they're all small trees. And he said, we can we can blow trees over double. But if you looked at the video, there's no movement in the tree. There's no mass damping there. There's the aerodynamics, which is a constant. So this is a static view, and you can see a tree that has adapted to its environment. Although the wind is there and it's there all the time, we can say, well, that's dynamics. It's really the forces are constant. So it's a nearly static, or in engineering we say quasi-static situation. And that's what the wind load equations calculate. And I mentioned the wind tunnel. So big trees and big damping. How am I going for time? Good. Oh yeah, 5 minutes to get through another 100 slides. So I'm going to go a bit quicker. So I think you get the point, and I've shown these before. Now, when you go to the literature, 80% of all the scientific literature on trees comes from forestry, wind loading on trees. That's where the money is, and that's where it finances research. And these are forest trees. Where's the mass damping on the forest trees? Pretty much not there. So all their conclusions of what the wind loads on trees are based on that simple model, because it's pretty much modelling their trees. But they're not the trees that we're dealing with. Okay, I'm going to go a bit quicker now because of time. This is tree failure analysis. I want to finish on the tilt sensors. Now this is some of Mathic's work, and we're saying the data in Mathic's. I would say there is no data in Mathic's work, and he's got into trouble because some of it is manipulated, if not invented, because it hasn't been peer reviewed in a scientific journal. It is a published book in German. So the sail area concept we've gone through. So let's have a look at the wind loads on trees. We've gone through that model of tree swaying. Here's some data. Now this is getting too much theory. All right, so I'll draw a coloured line. That's the wind. These are wind gusts coming, and it goes up to 60 kilometre an hour wind. That's what the best I measured in about 8 years of measuring data from a PhD. So 80 kilometres. So if we plug that in, or 60 kilometres, if we plug that into an equation, is that happening all the time? No, but it does come in gusts. Now have a look at the tree's response. There's the tree. This is what I measured. This is published data. What's happening? I still look at that and ask that question. I don't know. I do know that a big wind gust did not mean a big tree response. The big wind gust didn't mean the tree's load. This is loading at the base of the tree. I know I've measured that time and time again. I try and draw a graph for a publication. I can't get a straight line. It's an all over the place graph. I'm thinking, what do I do with that? I don't know. What is being done, and I haven't got time to show you some research papers, they average it. So instead of taking readings 20 times a second, they average it over a minute, so they get one dot. So an average might be a straight line across here, and they lose all that dynamics. What I think's happening here is the branches take some energy, get their sway up. And if you notice, collectively those branches are swaying. These are branch frequencies up and down, not tree frequencies. And I do a frequency analysis, that's all very theoretical. But later, for the next 10 seconds, the loading is increased but gradually comes down. So the tree is filtering that load. It's dampening it. How is it dampening it? Well, that's the complex thing, and I'm suggesting it's tilt sensors. So, I'm suggesting it's mass damping. So I want to finish on tilt sensors as an introduction to later presentations. Tilt sensors are small electronic devices that go on the tree and measure the tilt. So these are two. This one's a German one, which is updated. This is an old photo. And this is one from Lockie. He lent me one recently from Yugoslavia. Is that right? Hungary. All right, close. Are you game to say the name of it? Pardon? Fuck, it's a very unfortunate name. Fuck off. FAKOPP or something. So you can't forget that. So I asked you to download this in your phone. I was trying to work out a demo for you, but I thought, no, download. If anybody has downloaded it, activate Physics Toolbox. You have more technology in your pocket on tilt sensors than is available for arboriculture. It's already here. And the phone has 3 tilt sensors to measure in that direction, which I'll call X, that direction, which I'll call Y, and that direction I'll call Z. So you tilt your phone around, and if you turn that on the Physics Toolbox and you can twist your phone around, it will measure in 3 dimensions the tilt of your phone, and if you put it up against the tree, you will measure something. I don't know its accuracy, and it is subject to vibration. There's an inclinometer in there, you measure in degrees, but the technology available to us today is astronomical. Here's the logic of my logic for developing the tilt sensor, which I haven't physically developed it, but this is the logic of it. And I have worked in Germany for a week with the company to fine-tune what they were doing. My logic is a stable tree that's well entered in the ground will oscillate about a point which I'll say is in the centre of the trunk. Not a leaning tree, it's a stable tree, so all the weight's distributed, it's even, it's mature, it's grown, it's got branches all distributed around. So it's going to sway around a central point. So if we look at all the forces, we'll see that the forces of the wind tend to twist the tree over, tilt it. It lifts on this side, so there's an upward force there. There's a downward force on the root plate. Now if you stand and push down on soil, the soil pushes back. Soil is very good under compression. Give you an example. You stand on sand, very strong. You lift sand up in tension, has no zero tension. Engineers with their calculations treat the tension surface of soil as 0 when it's wet. You can pull it apart, it does have a bit, but we assume it's 0. So what I've found and what I'm saying and what the literature supports is the first thing to fail is the soil under the root plate cracks, opens up. That's the first thing. And it happens about 0.6. Now this has been reported many years ago as the first failure point during static pulling tests when people put a microphone, before computers, they put a microphone in it. And that reference comes from Coots, 1983. And there's my diagram, and there's his diagram from his paper. And that's what he's saying. So the first thing is a crack under the soil. So that's, I've observed that and I support what Coots says, and that's what I think happens. So that once that happens, maybe no roots have failed. Now I know there are some root experts here, so I'm not contradicting that, and I'm simplifying it. I know there are sinker roots, and roots aren't all the same, and particularly forest trees and trees planted do differ. Forest trees have more sinker roots. Plants grown from seeds have different roots, I know those, but I'm simplifying in general. And this, during static pulling tests, was a picture I took after a static pulling test, and it wasn't until some time later I realised that there's a bare spot there. Now, and it's not under the centre of the tree, it's on the opposite side to where the pulling test. Is that evidence that probably that's where the first failure did certainly crack there? We didn't measure it that, but if you observe the trees overfallen, especially urban trees, not forest trees, you'll often see there's a flat spot under the root plate. And in general, urban trees probably the roots only go down to where the oxygen finishes, which is about 600 millimetres. So that happens at about 0.6 degrees, and then failure is progressive, and that's what I've measured in trees and winds. And it could be that we get that failure. I think water can go down there sometimes. There's lots of rain and pounds. You hear of people in the literature talking about pounding. So that's like a high pressure hose eroding the soil and pumping it out, so the gap's just going to get worse and worse. And about 4 degrees is the maximum, and that's based on the Leaning Tower of Pisa, by the way, which is leaning at 4 degrees and is still standing. So that's where that number comes from. It's not a clear-cut thing, but after 4 degrees I think, well, you know, that's enough, and that's when failure is imminent. So that's where the tilt sensor idea comes from. If we can measure the tilt, does anybody know the limit of tilt according to the static pull test, when you stop the pull test? It's 1/4 of 1 degree, 0.25 or 0.25 degrees. So a lot of my work started saying, let's go out and measure it, wait for winds and see what happens in nature. And trees regularly get up to 0.6 with no problems. So the static pull test is 0.5. Trees regularly experience much more than that. So basically, I think this will be my last slide for time. I think my message is failure is not all at once. It may be sometimes, like those trees in Sydney we saw, they might have been working on, some trees do fail all at once, but generally root fatigue might be important. So it's possible with large stable trees to measure something, and I think all my wind load work, I don't know what to do with it. I don't know how to translate that into a practical outcome, but the tilt sensor gives us something that is a measure of stability, and I think it's got potential. It's not the answer, and still won't predict failure, but it will confirm a tree is stable and doesn't have to come out. And I've used that on several trees, and the people have decided to keep the tree. One in Tasmania, and that's a publication. There were 5 Norfolk Island pines in a row. One was moving, obviously, and they are iconic. They used to be used by the sailing ships as beacons to come in. So it's a Burnie, and they were very concerned that if one was cut down, it wrecks the whole lot. And I put the tilt sensors on it and measured that tree was not going beyond the normal. But then I was the only one that ever bothered to go and measure the tree. Everyone would see it. You could see a crack opening up. I thought, it doesn't make sense. So I started digging down, and what had happened years before I came along is the trees were in natural environment, and then they paved over the whole lot and made it level. So the root plate was down here. So what was obvious as movement was there, but the root plate wasn't moving. But I didn't put the sensor right down at the base. I put it about 600 or 400 mils above. So it's been useful to confirm if there's construction or worry about a tree having to be removed that you don't want to remove. It really probably confirms stability more than predicting failure. But it's also useful around an area with many trees to put them on many trees, because a windstorm goes through, and this has happened on a site in Monash University, where several trees flew over. So we knew it was a big wind, but the tree in question didn't. So it confirmed that this tree didn't have to come out. It gave you some confidence to say this tree was stable. So tilt sensors have been around a long time. We've got a lot of technology now in our pocket. I think they've got some potential, and we'll talk about that later in the day, but I'll finish on there and ask for any questions.
What's the time frame to get a good reading off a tilt sensor? Like, how long do you need to have it attached for?
When's the next wind? Now look, one of the biggest problems of any technology out in the field is power. Shane got all enthusiastic last week that he loaded that software up, and he was out in the field and he's texting me, oh, I've run out of batteries. And you put a sensor on today and you've got to wait for, when's the next wind going to blow? And you're an arborist and need to get a report back to the construction company by next week, or the tree's coming out. That's where the static test is a diagnostic tool. And this is a limitation of the tilt sensor. But that tree's been there a long time, decades. The construction guy needs an answer next week. The tree's evolved over decades, and with heritage and valuable trees, you know, there's a time imperative in business that doesn't match these tilt sensors. So they haven't sort of been taken up as quick as I thought they might. But equally, I'm yet to see data out of the latest versions because they're not that simple to use, I don't find. I have an people who own a dog, your dog's been microchipped under its skin so it can be recognised. I imagine tilt sensors get miniaturised and you inject them under the bark, and there you go past and check them with your phone, and then if there's been a wind you go and download the data. That they don't log until there's a data there. So they're probably at a beta level of development at the moment is what I picture them. And again, they'll be connected back to a central location, and you'll get a red dot saying, oh, this tree's starting to move more than it used to. So and that's another thing, the history of the tree last year to this year is very useful because you're not just dealing with one tilt data sensor on one day in the still air. You can see its history and say, oh no, it's moving more than its neighbours. But see, on a coastal golf course like this, you're likely to have different soil types. You'll have a sandy soil down there and clays over there, and you will get different movement. Yeah.
The drag coefficient seems to be used pretty regularly from an engineering and a town planning point of view.
On trees?
On justifying the removal of trees. How can that be changed? I mean, that's pretty commonly used in VCAT tribunals, I guess Land and Environment Court in New South Wales and so on, and it seems to be accepted engineering numbers and science.
I wish I knew the answer. I could say I was doing a PhD at Melbourne University, and on the car park at Melbourne University, the underground car park, trees are built on the roof. And they were really worried about the trees getting too big and damaging. It's a heritage listed structure. It was used in the filming of Mad Max, so they're very proud of it. So I was sitting on a committee, and they had a commercial engineering consultant who charged them $10,000. This is 20 years ago. I wasn't being paid. And he wrote a report, and he did a wind load calculation using drag coefficients. And I was the only one stupid enough or brave enough to ask the question, what does that mean? And he said, I have no idea. It's just got the calculation that he did and put in. So that's where we're at. So they wouldn't give me any money for research. They paid $10,000 to a consultant engineer who used that equation, and the committee would use his work, but not mine, and they paid him and they wouldn't pay me. I'm in the same boat as you. I think you can challenge it at the moment, but to challenge it, you have to construct an argument. I've been wondering, is it worth writing an argument, writing a scientific paper that can be used to challenge it? Because I can do that now. I have enough knowledge to do. I don't know. And my earthquake engineering consultant's also an expert in that field, so I do it with him. And also, the world president of the Wind Engineering Society is a man called Dr. Holmes, who lives in Melbourne. He's a friend of my supervisor, and I've had lunch with him, and I asked him about it. He said he'd be very interested to know, because all the wind load, now he's the president of the world codes. He writes the code. You have a look in the Australian Wind Code. Holmes is the reference, Holmes. And he said, we know nothing about the wind near the Earth's surface, so from 10 metres below, 30 feet below, we don't know what's happening. It's because it's turbulent flow. But that's from the horse's mouth, but it's not in writing, it's not in the wind code.
So we're stuck with it for a while.
Well, you asked how to change. I don't know how to change other with knowledge, yeah. Could I show you, to answer that question, could I show you a research paper? Okay, quick answer to Ben's question. We're in court. How do we challenge what people are saying in their calculations? Okay, I don't know. So this is 2025. This year, Journal of Wind Engineering and Industrial Aerodynamics, mean and maximum two-dimensional wind force on an open-grown tree. Written by Nicholas Angelo, don't know, Barry Gardner, one of the most eminent researchers in forest engineering. Forestry trees. Remember forestry trees? Open growth trees. Okay, read, text. I just look at the pictures. There's the tree. Little tree. Where's the mass damping? It's all statics. Have a look at the wind, the resources on measuring the wind. Oh, let's go and measure the wind around a tree. Wind anemometers.
You say static, but there's always load on there because of gravity and length and leverage. So it's not really static because it's like a preloaded spring the whole time. Right?
When you say it, what is it?
Tree and its branches.
It's an open grown tree.
Yeah, but there's still load because there's gravity and there's length.
Oh, that's true. They measure all that. But with their sensors, they're waiting for a wind to come. This is a title, The Wind Loads on an Open Grown Tree. I'm just saying the tree is a small one.
Yeah.
That's all I'm saying?
Yeah.
Yes? It's not a big tree, it's a small tree. And they've got huge resources, but they chose a small tree. So let's have a look at the data. This is where it's at. Good question. Let's have an argument about it, but let's just start with the paper. Yeah, because what's it saying? So we go through and looks a bit theoretical. Oh, there's a graph. Don't really want that. There's another one that looks, don't know. And then I get to that. That's very similar to the images I've put into my PhD thesis and published, and that's showing the readings on their sensors at 20 times a second, 20 hertz. So you see the tree swaying around. That's probably over a 10-minute period and the wind's blowing from this direction. So this to me is really good data. Okay, so I said, okay, they've got some good data on a small tree, but they've got it. I can use that. But then what they do is they draw these lines, 1 minute mean force. 1 minute mean, meaning 1 minute average. So whatever is happening on the tree, they wait for a minute and average out the forces and then plot 1 point. And they do that in order to get a nice curve that they can publish and confirm the drag coefficients. So this is supporting the equation for the drag coefficients to show that you can use the drag coefficients, but they're taking 1 minute average samples, and averaging changes the dynamics to static. This is what I got this minute, average over that minute, so all that variability we take out. So it's a quasi-static, it's as if it was static analysis, and you can draw a straight line. Because my other slide, I haven't got time for my second presentation, I just published the raw data. It's all over the place, and I say, I don't know what's happening. There is no relationship between the wind, there's no linear relationship, direct relationship between the wind and the force on the tree. It's an indirect one. I've been under a 40-metre manna gum in Healesville in a big wind with my computer going up and down in real time, and I hear a big wind go through the tree, and I'm wondering if I'm safe to be under there. No response on my computer for more than a second and a half. It took a second and a half for that, whatever was happening up there, to come down that big, massive trunk and register on the sensors. So there's a lot of flexibility and, I don't know, hydraulics in these trees, but I can't say what that means other than it's not a direct linear. That straight line I would challenge, but that straight line is based on that drag coefficient. So you can't really argue against that in court, and that's where the current research is, but it's not on trees like with big trees with big branches. It's not on those trees, and they're scaling up the results. And you have to mount an argument for why those results on small trees don't apply to these trees, and we haven't got a legal argument for that yet. So a lot of what I'm saying is based on some science, but there's no direct, firm thing you can hold on to say, yes, this is occurring. It's gradually, there's an idea coming. It's a bit like the axiom of uniform stress, but probably with a bit more science behind it, this mass damping. And it's not just mass damping, but it's a contributor to the overall tree. So I think I might finish there.
Thank you, Ken. Stevie?